Okay, lots of examples here. And some of these are going to be ones where you may not want to like really work out all of the patterns. The key is just to know where they're going towards, like what is the limiting process on all of these. So, for example, you might have something like the pattern is 2 to the n plus 10 over 2 to the n. There's your pattern. And sometimes I write the curly braces and sometimes I don't. Today I'll try not to be lazy, so I'll do this and we'll say n starts at 1. If it's not written, that's typically what the default is. There may be some patterns where you can't actually plug in 1. You might end up accidentally having a division by 0 or something, so you have to move the n over until you can start. But again, remember, this is an infinite sequence, so if you start a little bit over in your list, it's okay. The key is what's going to be the limit on all of this. So if we did try to write some of this stuff out just for kicks, let's see, A1, we plug in our pattern A1. So we'll get 2 to the 1 plus 10 over 2 to the 1. So that's what that means. So I will get 12 over 2, which in this case happens to be 6. So I started 6. So maybe we can draw some of this stuff. So up here at 6, there's my A1. Start up there, n equals 1. At 2, so let's see, we get 2 squared plus 10 over 2 squared. So I just plug in 2 where I have n, and I will get 14 over 4, which is what? That's 3.5. So 3.5. So at 2, I'm a little bit above 3. So there's my A2. 3.5. And I just keep going. I'm probably only going to do one more. Let's see, 2 to the third plus 10 over 2 to the third. And the answer is 18 divided by 8. And that answer is 2.25, 2.25. I think. Yeah. 2, 2. Now, I don't mean to deceive you that it's like, oh, maybe the answer, 8, 3. It's going to 0. Well, let's plug in something that's a lot bigger, a to the, say, to the base of 10. So we have 2 raised to the 10th power plus 10 over 2 raised to the 10th power. Let's see, what's 2 to the 10? So it goes 2, 4, 8, 16, 32, 64, 128, 256, 512, is that 10? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So one more, 10, 24. So we get 1,034 over 1,024. So that number is approximately 1 point something. I don't know, 1.01-ish, something like that. So maybe you can see even at this stage that this plus 10 right here, after a while, is going to be 2 raised to a number, which gets big, plus 10. That 10 is not going to do very much. So if I thought about that, probably the limit, this plus 10 is not going to matter after a while. So if we look at the dominant terms, 2 to the n is the dominant term on the top. 2 to the n is the dominant term on the bottom. So we just get 2 to the n over 2 to the n eventually, and so the limit should be 1. So the limit equals 1, looking at dominant terms. And I just talked it out. If you didn't want to do dominant terms, then the other thing you could do is just divide. So this is what happens if you actually do the division. So an will be 2 to the n over 2 to the n plus 10 over 2 to the n. And so my pattern is now 1 plus 10 over 2 to the n. And now that one, you're like, okay, I see. I get the 1, and what happens to these terms right here, as n gets really big, this term gets really small. In fact, the limit of this term is small. 10 divided by something that's getting really big. And so if you did the division, you could then see that the limit was 0 and then plus 1. So the answer is 1. So the point is there's kind of like this asymptote here at 1, that these numbers are getting closer and closer and closer and closer as you go down. So the limit is equal to. Final thing is it also really does look like a L'Hopital's rule, right? You have 2 to the n plus 10 over 2 to the n. It looks like infinity over infinity. Can I take a derivative? Well, it's not a continuous function, but you can think about it. So L'Hopital's rule does, I don't want to go into too much here, but you can really think of this as do L'Hopital's rule, and we'll get the derivative of 2 to the n, which is 2 to the n natural log n, or 0, and then 2 to the n natural log n. And so this does end up being just 1. So L'Hopital's rule does apply. You've sort of smoothed it with x's in, then used L'Hopital's rule, and then said it's basically the same thing. So any of that kind of reasoning can work out. Which actually will help if I say this is limit as n goes to, no, I didn't want to do that. Let's try a sub n. Well, I'll come back to that. A sub n equals, how about this? N minus 1 over n minus n over n minus 1. And now I'm going to have, I can't start n equals 1 because I would be divided by 1. So let's start at 2. Start at n equals 2. So what happens there? So let's just start doing pattern. A1, so plug in 1, you will get 0 over 1 minus, I can't plug in 1. I said I couldn't plug in 1. Divided by, I have to plug in, start at 2. So I'll get 1 over 2 minus 2 over 1. So that is negative 3 halves. So it's a half minus 2, so negative 3 halves. If I plug in A3, or 3, plug in 3, I'll get 2 over 3 minus 3 over 2. All right, what is that? Now it's a certain number of sixths. It's 4 over 6 minus 9, minus 5 sixths, minus 5 sixths. Okay, let's do one more. Then we get 3 over 4 minus 4 over 3. 3/4 minus 4/4. The common denominator there is 12. Multiplication by 3, multiplication by 4. 9 minus 16. Get negative 7 twelfths. It's kind of hard to see what's happening. So what do I, what's the pattern here? So what I want to do is I want to just combine them. Combine the fractions. In the next section, I'm going to want to separate the fractions. In this one, I'm going to want to combine them. Just because then I'll get one term, and it might be easier to see what's going on. So combine the fractions. Common denominator is n times n minus 1. So I multiply the first one by n minus 1 over n minus 1. Multiply the second one by n over n. And let's see what we get. We get a common denominator of n and n minus 1. So multiply this out. We'll have n squared. The middle term is minus 1, so minus 2n, and then plus 1. That's the first one. And then the second one is minus n squared. So my pattern now is negative 2n plus 1 over, because the n squares will cancel, over n times n minus 1. Or if you prefer, it's minus 2n plus 1 over n squared minus n. So you can verify that you get the same thing. You plug in 2, the top will be 3, the bottom will be 4, it'll be negative, we'll get 3 over 2. What happens when I plug in 3? If I plug in 3, I get negative 6 plus 1, that's negative 5. On the bottom, I'll have 9 minus 3, which is 6. Okay, so this formula looks like it's giving me the same answer, so I must have done. I think I did something right. So now I think it's easier to see what is the limit as n goes to infinity of negative 2n plus 1 over n squared minus n. And here again, it looks like infinity over infinity, so you could use L'Hopital's rule. You could look at the dominant terms. Maybe the dominant terms are, what are the dominant terms? The dominant term is n squared. On the top, it's negative 2n. So if you try the dominant terms, idea, I think it's not a bad idea, is with the limit as n goes to infinity, negative 2 over n. So you have 2n on the top and n squared on the bottom. One of the n's cancels, and you get that, and that answer is 0. As you plug in bigger and bigger numbers, they're only going in the denominator now. So if you were to plot more and more of these things out, it's annoying because it's a fraction. And how did you do it over here? You had to got a common denominator anyway. So let's just find the common denominator from the beginning. And you can see the limit is 0. So if you were to plot these things, they would be 0. They would, in fact, be coming up like this. The numbers, if you were to plot them, would be coming up that way. So they are coming into the 0 line, but from the negative. I think we'll do one more here, and then we'll shift over to what happens when you start adding these things together. So, and this is a little bit of a trickier one. An is 1 plus 2 over n raised to the 2n power. So that is my pattern. I'm trying not to be lazy today. We're doing this sequence starting at 1. Again, we're going to do a limit, so it doesn't really matter where you start because you're going out to infinity, but let's see what happens. What do I want to put this here? I'll just do it across here. What is A1? What's the first term? I plug in 1. 1 plus 2 over 1, so that's 3. Plug in 1 to the power, I get 2. The answer is the first term gives me 9. But that's probably not going to necessarily help. Look at the last problems. We started way out, and then we actually eventually got to the limit. So really, we probably want to just plug in some really big numbers, but and I will in a second. So A2 will be 1 plus 2 over 2, so that's 2, but then I'm raising it to the 4th power. 2, 4, 8, 16, so that's 16. If you keep going, 3, 4, 5, what if we did like A10? It would be the 10th number in this sequence. I plug in 10, and so I get 2 over 10, which is a 5th. So I'll have 1 plus, I'll just write it like this. So it's 2 over 10 raised to the 20th power. I'm plugging an n in both places. So that's going to be 1, and that's a 5th. The 5th is 0.2, so that's 1.2 raised to the 20th power. And we'll go ahead and do that one. 1.2 raised to the 20th is around 38.338, approximately. It still doesn't necessarily help. I mean, we want to let this thing go to infinity. So the key is what's the limit as n goes to infinity of 1 plus 2 over n to the 2n power. And now I do have to go back and use some L'Hopital stuff, because what happens as n goes to infinity? That's going to 0. So the whole interior is going to 1. But the power is going to infinity. So this looks like an infinity power, 1 to the infinity. which is clearly not 1. I mean, it's not going to be 1 for sure. It's an indefinite form. And so you have to figure out how to do this with L'Hopital's rule. And so this is definitely 1, just like we did before, where you do E natural log. And then we have to manipulate this. So you bring the power down, and this looks close, except the problem is now this looks like an infinity times 0 in determinate form. So we're not quite there yet. So you have to do this reciprocal idea. I'm going to do it again. Okay, so we get E. We do the reciprocal idea again. 1, 2 over n, 1 over n. And now if I do this, this looks like 0 over 0 in the numerator, so I can use L'Hopital's rule on that. I get the limit, n goes to infinity. E to the 2, I take the derivative of the top, which is 1 over 1 plus 2 over n, multiplied by the chain rule on the bottom, which is going to be minus 2 over 2n, all over the denominator derivative, which is negative 1 over n squared. I guess I'll go ahead and clean that up a little bit. Limit as n goes to infinity. I've got E. What else do I have? These n squareds will cancel. The negatives will cancel. The 2 and the 2 will give me 4. Simplified. And then on the denominator, I've got 1 plus 2 over n. I'll clean all that up right. Here's what we get. So as n goes to infinity, this term right here goes to 0. So I will get E to the 4. That's the final answer. And if we put that back in the calculator, that 4, E to the 4th is approximately 54.59. So instead of going through all this mess and trying to figure out what the answer is, boom, we had to go out even further in order to get to this point. So 54 point E to the 4th is the final answer on that one. It's definitely not expected, but it converges to 54.59. Okay. I know we just did a little bit there, but let's do just one more quick break, and then so we can finish sort of strong, because we're on to 8.2, which is now not just sequences, but we're going to be adding them up. So say 11:05. See you back here in 5 minutes.